Have you ever wondered what secrets the universe still holds? Imagine stars so massive they could swallow our solar system, planets where fluffy glass rain falls, and black holes that can trap light itself. Come witness galaxies colliding in slow motion, the invisible forces that shape reality, and mysteries so bizarre they'll make you question everything you know. From the sun to the stars, we'll uncover the energy pathways driven by plasma turbulence and magnetic fields. It's a long story, so let's start it in a dream. Before we begin, don't forget to like and share. Space is not a static void but a dynamic, constantly evolving entity. It shapes everything we observe, from galaxies and stars to the fundamental structure of reality itself. To understand how space was created, we must step into the intersection of physics, cosmology, and philosophical contemplation. This is a journey to the very genesis of existence. The origin of space is tied to the Big Bang Theory, which describes the beginning of the universe approximately 13.8 billion years ago. At the time of the Big Bang, space-time, energy, and matter were created in an unimaginably dense and hot initial state. However, the term explosion is somewhat misleading. It wasn't an explosion in existing space, but the appearance and expansion of space itself simultaneously. To grasp this concept, we must transcend the everyday intuition that space is a fixed, unchanging background. Space and time are fundamentally interwoven, forming the unified entity known as spacetime, described by Einstein's theory of general relativity. Before the Big Bang, the space or time we understand did not exist. As we approach the infinitely dense point, the source of cosmic expansion, physical laws break down. Therefore, asking, what was before the Big Bang, is problematic because time itself began at that moment. Without, before time, the question loses meaning, just as you cannot speak of north of the North Pole. At the moment of the Big Bang, space began from a nearly infinitely small region and rapidly expanded. This expansion was not matter moving into a pre-existing void, but the fabric of space-time itself stretching. To visualize this, cosmologists often use the analogy of inflating a balloon. The points on the balloon's surface represent galaxies separating as space expands, and the surface expands, but there is no inside or outside of the balloon. Space itself is all-encompassing. A key process in the early universe is called cosmic inflation, which occurred in the first fraction of a second after the Big Bang. Inflation saw space expand exponentially, increasing in size by an incredibly large factor in an unbelievably brief moment. This extremely rapid expansion smoothed out irregularities in the universe, creating the nearly uniform fabric of space-time we observe today. Inflation also amplified the quantum fluctuations, tiny, random ripples in the energy density of space, which later became the seeds for the formation of galaxies and the large-scale structure of the universe. One of the most fascinating properties of space is that it is not truly empty. Quantum field theory asserts that even the vacuum is teeming with activity. At the most fundamental level, space is filled with quantum fields, where particle-antiparticle pairs briefly pop into and out of existence. This is known as quantum foam. This quantum foam underpins the spacetime fabric, suggesting that a deeper, more complex reality is hidden beneath the universe's smooth surface. These fluctuations may have played a critical role during inflation, being amplified to potentially explain the clumping of matter distribution we observe today. Einstein's theory of relativity revolutionized our understanding of space, showing that it is not a rigid framework but a flexible entity that can be warped and molded by mass and energy. Massive objects like stars and galaxies distort the spacetime around them, creating the effect we perceive as gravity. These distortions cause light rays to bend and time to slow down near massive bodies, phenomena observed in events like gravitational lensing and time dilation near black holes. Space is not a passive background, it is constantly being shaped by the matter and energy within it. The creation of space is also intimately linked to the concept of the cosmological constant, which Einstein introduced into his equations to describe the energy density of the vacuum. Initially regarded as an error, this constant has regained importance in explaining the accelerating expansion of the universe. This acceleration is attributed to dark energy, a mysterious force that permeates all space and pushes galaxies apart at an increasing rate. This suggests that space is not merely a stage for cosmic events but an active participant in cosmic evolution. The cosmic microwave background (CMB) radiation provides a window into the early universe and the genesis of space. This faint glow, detectable from every direction, is the afterglow of the Big Bang, an imprint left at the moment when the universe transitioned from opaque to transparent, and photons decoupled from matter. The CMB captures a snapshot of the universe when it was only about 380,000 years old, showing a nearly uniform energy distribution along with subtle fluctuations. These ripples correspond to the minute density differences shaped by quantum fluctuations during inflation. The CMB confirms that space has been expanding and evolving since its creation, providing key insights into its origin. The creation of space also raises profound questions about its underlying nature. Does something deeper exist beneath space-time? Some theories propose that space may emerge from more fundamental structures, such as vibrating strings or quantum spin networks. In these models, the space we experience is a construction of higher dimensions, and the familiar three dimensions of space plus one dimension of time may be only emergent properties of a deeper, multi-dimensional phenomenon. The multiverse hypothesis takes this idea further. Our universe may be just one of countless universes, each with its own version of space-time and physical constants. If true, the creation of space in our universe would be just one instance in an infinite series of cosmic births, each governed by different physical laws. While these ideas remain speculative, they offer tantalizing possibilities for understanding the origin of space in a broader context. Another perspective comes from loop quantum gravity, which proposes that space is not a continuum but is composed of discrete, finite pixels. According to this theory, spacetime is quantized at the Planck scale, made up of incredibly tiny, indivisible units. This idea challenges the classical concept of smooth space and opens up new avenues for understanding the creation and structure of space. The creation of space also involves philosophical considerations. If space and time emerged from the Big Bang, what does this imply about the nature of existence? Is space a fundamental category of reality, or is it a construct born from more fundamental principles? These questions push the boundaries of human understanding, requiring both scientific exploration and metaphysical reflection. Stars, those seemingly static points of light in the night sky, are actually dynamic, constantly changing celestial bodies. One particularly fascinating internal phenomenon is stellar seismology, which refers to massive, unimaginable scale oscillations or waves that ripple through a star's interior, similar to how seismic waves travel through the Earth. To understand stellar oscillations, imagine dropping a pebble into still water. The spreading ripples are like the waves traveling through the star's interior. When stellar oscillations occur, these waves reveal intricate details about the star's internal structure. Thus, stellar seismology has become one of the most powerful tools for studying stars. The roots of stellar oscillation lie in sudden changes in the star's internal structure. Deep within a star, gravity constantly pulls matter inward, while nuclear fusion in the core provides outward pressure, locked in a continuous struggle to maintain equilibrium. Should any disturbance upset this balance, such as a sudden change in core temperature or density, the star will undergo a tremor. Depending on the star's size and structure, these oscillations can last for hours or even days. These oscillations are invisible to the naked eye but can be detected by observing tiny variations in the star's brightness. The ripples on the star's surface cause extremely subtle changes in the light it radiates, much like a bell's tone changes slightly when it vibrates. By precisely analyzing these minute photometric differences, astronomers can determine the frequency and amplitude of the stellar oscillations. The field that studies this is called asteroseismology, and it has completely transformed our knowledge of stars. A key discovery of asteroseismology is that stellar tremors open a window into a star's interior structure. Typically, we can only see the star's outer layer, the light-emitting photosphere, but asteroseismology allows scientists to peer into its hidden interior, much like a doctor uses an ultrasound to view internal organs. For example, by studying the oscillations of red giant stars, astronomers have been able to understand the structure of their cores and how energy flows from the core to the surface. This information helps us refine models of stellar evolution, clarifying the paths stars take as they age and die. Stellar oscillation research has also revealed a star's chemical composition. Different elements in the core produce different oscillation modes, just as different materials emit unique sounds when struck. By analyzing these patterns, astronomers can infer the proportions of hydrogen, helium, and heavier elements in the star, which is vital for understanding the star's early life stages and its ultimate fate. One of the most spectacular implementations of stellar oscillation research came from NASA's Kepler mission. Originally tasked with searching for exoplanets, Kepler continuously monitored the brightness of hundreds of thousands of stars, capturing vast amounts of oscillation data, becoming a treasure trove for asteroseismology. Scientists have used this data to find that some stars exhibit solar-like oscillations, vibrations driven by outer convection layers that are strikingly similar to phenomena observed on the Sun. Stellar oscillations have also revealed how magnetic fields affect stars. Strong magnetic fields alter the way waves propagate inside a star, creating unique oscillation patterns, which is critical for understanding stellar magnetic phenomena. Magnetic fields govern violent events like solar flares and coronal mass ejections, and these events significantly impact nearby planets and our space technology. Beyond improving the understanding of individual stars, stellar oscillation data has broader applications. For instance, studying the oscillations of stars at different evolutionary stages helps refine stellar evolution models. These models are used to predict the long-term behavior of stars of different masses and compositions, which is also relevant to the origin of chemical elements in the universe, as different types of stars forge different elements through nuclear fusion. Asteroseismology has another important practical application: accurately determining a star's age. Knowing a star's age is essential for understanding the history of its planetary system. A star that is too young may still have planets forming, while one that is too old may no longer be habitable. Asteroseismology helps us accurately place stars on this timeline. Another exciting frontier is the study of oscillations in massive stars to probe their ultimate fate. Massive stars typically conclude their lives in spectacular supernova explosions, leaving behind neutron stars or black holes. By analyzing the oscillations of these stars, scientists can learn about the internal conditions just before the explosion, thus understanding how they disperse heavy elements into galaxies and shape the cosmos. Even neutron stars, the ultra-dense remnants of massive stars, can undergo seismology-like phenomena called starquakes, which occur when the neutron star's rigid outer crust suddenly slips. Studying starquakes gives us a glimpse into extreme physical conditions where matter density exceeds the limits of our understanding. Stellar seismology also has a certain poetry. It reminds us that stars are not cold and immutable but continuously evolving systems that respond to internal and external forces. Because of this dynamic nature, stars remain endlessly fascinating, with every new discovery revealing another layer of complexity. Stars are born in molecular clouds in space, gigantic regions of gas and dust that span light years across galaxies. They are the stellar nurseries. Imagine them as the hazy outlines of clouds on Earth, but instead of water vapor, they are primarily made of hydrogen, mixed with smaller amounts of helium and other elements. These clouds drift quietly in space until some disturbance upsets the equilibrium, perhaps a shockwave from a nearby supernova or the gravitational pull of a passing star. Consequently, some regions within the cloud begin to collapse under their own gravity. This is the first step in star formation. As the gas collapses inward, it heats up, and a protostar forms at the center of the collapse, a luminous, dense core that will eventually grow into a true star. Diagram of star formation from molecular cloud to protostar. You can think of it like squeezing a lump of clay tighter and tighter, making it denser. In the protostar's core, the compression is intense, and the temperature reaches millions of degrees, enough to ignite nuclear fusion. At this point, hydrogen atoms are fused together to form helium, releasing vast amounts of energy. This outward pressure balances the inward pull of gravity, and the star stabilizes. Our Sun underwent the exact same process billions of years ago. A young star is encircled by a residual disk of gas and dust called a protoplanetary disk. This is the starting point for a planetary system. Imagine it as a potter's wheel where clay is spun into a bowl. Within this disk, dust grains collide and stick together, growing into larger clumps that gradually evolve into planetesimals, the building blocks of planets. Some planetesimals merge to form planets, while others become satellites, asteroids, or comets. Diagram of a protoplanetary disk showing accretion and planet formation. The temperature structure within the disk dictates which types of planets will form. Closer to the star, where temperatures are high, rocky planets like Earth and Mars form. Farther out, where temperatures are low, gas giant planets like Jupiter and Saturn form, possessing thick hydrogen and helium atmospheres. This inner rocky, outer gas division shaped the rich diversity of worlds in our solar system. However, the area around a nascent star is not tranquil. Young stars emit intense radiation and stellar winds that blow away surrounding gas and dust, sculpting the architecture of the planetary system and determining the raw materials left for planet growth. For example, the Sun's powerful radiation likely cleared out a vast amount of gas in its inner region, allowing Earth to become a rocky planet rather than a gas giant. Observations of other stellar systems reveal that the diversity of planetary systems far exceeds our intuition. Some stars have planets tightly packed together, with orbital configurations that look like alien jigsaw puzzles. In other systems, planets orbit far from the star along large eccentric paths. This variety demonstrates that the process shaping planetary systems is both universal and highly variable, profoundly influenced by the unique conditions of each protoplanetary disk. Directly imaging the structure of these disks using telescopes like the Atacama Large Millimeter, Submillimeter Array ALMA is one of the most exciting directions in this field. We have seen disks with gaps and rings, which are believed to be the paths cleared by planets in formation as they gather matter, a cosmic construction site where planets are the workers and the protoplanetary disk is the raw material. Turning our attention back to our own solar system, approximately 4.6 billion years ago, the Sun collapsed from a cloud of gas and dust in the Milky Way, and the surrounding disk gradually gave birth to planets, moons, and small bodies. Over millions of years, gravity pulled planetesimals into increasingly larger clumps. The inner disk, rich in metals and silicates, formed the terrestrial planets like Mercury, Venus, Earth, and Mars. The outer disk retained more condensable ices, facilitating the formation of the gas giant planets and icy bodies like Pluto. The remaining construction debris was not wasted. Comets and asteroids, as remnants of the early solar system, act like time capsules recording the environment of that nascent era. Studying these bodies allows us to look back at the formation conditions from billions of years ago. Planetary migration is another key factor. In the early stages of a system, planets can shift their orbits, moving closer to or farther from the star. This can dramatically reshape the entire system, pushing minor bodies into unstable orbits or even ejecting planets from the star system to drift into interstellar space. In our solar system, the movement of Jupiter may have profoundly influenced the distribution of the asteroid belt and the formation history of the terrestrial planets. The discovery of exoplanets has further deepened our understanding of these processes. Hot Jupiters, gas giant planets scorching close to their stars, force us to revise traditional models of how planets form and migrate. Despite immense progress, many puzzles remain unsolved. What determines how many planets a system will have? Why do some systems produce Earth-like worlds while others do not? How does the environment of a star's neighbors shape the final architecture of the system? Every new discovery brings us closer to the answers, but clearly, no two planetary systems are exactly alike. Supergiants are rare and extraordinary celestial objects that push the boundaries of what a star can be. They possess enormous mass and astonishing luminosity, often shining millions of times brighter than the Sun, with radii extending hundreds or even 1,000 times that of the Sun, making them the brightest lights in the universe. However, such brilliance comes at a cost. Supergiants burn their nuclear fuel at a furious pace. Compared to stars like the Sun, which live for tens of billions of years, supergiants often survive for only a few million years before meeting a dramatic cosmic end. Like all stars, supergiants are born in the dense regions of molecular clouds, but what sets them apart is the sheer mass they accumulate in their early stages, typically starting at least 30 solar masses, sometimes reaching hundreds. Such immense mass leads to extreme core temperatures and pressures, driving a rapid nuclear fusion process and accounting for their dazzling luminosity. From the moment they ignite, supergiants are destined for a turbulent life. The nuclear fusion in the core generates tremendous radiation pressure, which maintains a precarious balance against the inward pull of gravity. Unlike low-mass stars, the immense weight of the supergiant's outer layers pushes the core to extreme conditions, making the system inherently unstable. Accompanied by this internal turmoil is an insane rate of mass loss. Supergiants shed mass at an astonishing rate through powerful stellar winds, blowing away the equivalent of multiple Earths every year. This continuously reduces the star's mass and size while exposing deeper layers where heavier elements are being forged. Instability is a hallmark of supergiants. Their outer layers frequently undergo violent pulsations, expanding outward and contracting inward in a cyclical manner. These pulsations can also eject massive amounts of matter, creating vast and complex surrounding nebulae. The famous star Eta Carina is a supergiant surrounded by the Homunculus Nebula, a relic of several immense outbursts during the star's life. These eruptions are not only spectacular but also reveal the extreme internal processes nearing the star's demise. As a supergiant approaches the end of its life, the core becomes increasingly unstable. The fusion of lighter elements progressively gives way to the fusion of heavier elements, with each stage shorter than the last, the final stages lasting only days or hours. The turning point comes when iron is forged in the core. Unlike lighter elements, iron fusion does not release energy, instead, it absorbs energy, causing the core to collapse under its own intense gravity. This core collapse triggers a chain reaction, culminating in a supernova explosion. The outer layers are flung into space with unimaginable force, and the core is compressed to extreme density. If the mass is suitable, it leaves behind a neutron star. If it is even greater, a black hole forms. Supernova explosions from supergiants are among the most significant events in the entire cosmos. The explosion releases energy that can momentarily outshine an entire galaxy, and through the supernova nucleosynthesis process, it forges various heavy elements, including gold, uranium, and others, which are then scattered into the interstellar medium. Over time, these elements are incorporated into new generations of stars, planets, and even life itself. Supergiants are therefore key contributors to the chemical evolution of the universe. Their remnants are equally compelling. If a neutron star is left behind, it may become a pulsar, acting as a lighthouse of electromagnetic radiation beamed out from its rotation. If a black hole forms, it may accrete matter from nearby stars, becoming a source of high-energy radiation. In either case, the death of a supergiant profoundly impacts its surroundings. The energy injected by supergiants plays a dual role in the galactic ecosystem. Powerful stellar winds and supernova shockwaves can compress nearby molecular clouds, triggering new star formation, but the same forces can also blow away gas and dust, suppressing star-forming activity in certain regions, creation and destruction proceeding hand in hand, demonstrating their far-reaching cosmic influence. Observing supergiants is challenging. They are rare, short-lived, and often located far away. Their extreme brightness also makes it difficult to resolve fine details. Fortunately, observational techniques in the infrared and radio wavelengths are constantly improving, helping us pierce through the dust and analyze the interaction between stellar winds and the surrounding medium. There are still unanswered mysteries. Why do some supergiants conclude their lives in a supernova explosion, while others seemingly bypass the explosion and collapse directly into a black hole? The answer may lie in a complex coupling of mass, rotation, magnetic fields, and chemical composition. Their erratic luminosity is also a clue. The irregular changes in brightness of many supergiants reflect the dynamic processes of energy transport and convection in their outer layers. Long-term monitoring of these changes offers a glimpse into the turbulent inner lives of these behemoths. Studying supergiants also has a macroscopic significance. In the early universe, massive stars were more common. Today's research on supergiants can simulate the environmental conditions of that era, illuminating the early chapters of galaxy formation and cosmic chemical evolution. It is fair to say that the very existence of supergiants challenges our understanding of stellar physics. Their size and luminosity push theories to the limit, forcing astronomers to continually revise their models. Every new discovery about supergiants is another crucial piece of the puzzle in understanding how stars and galaxies have evolved over billions of years. The universe initially possessed only the simplest elements: hydrogen, helium, and trace amounts of lithium, formed during the primordial nucleosynthesis in the first few minutes after the Big Bang. Yet, today we see a universe rich in heavier elements: carbon, oxygen, iron, gold, and others, which are indispensable for the formation of planets and life. These elements are forged in the cores of stars through stellar nucleosynthesis. Diagram of the onion skin structure in an evolved massive star. Within every star, nuclear fusion is the engine that drives its existence. When the immense gravitational pressure in the core forces atomic nuclei to collide and merge, energy is released. In the Sun, for example, the process begins with hydrogen. Under extreme heat and pressure, the repulsion between positively charged protons is overcome, and hydrogen nuclei fuse into helium, releasing light and heat that sustain the star's brilliance. In more massive stars, fusion does not stop at helium. As the star ages, the core becomes hotter and denser, allowing it to continue smelting heavier elements. Helium fuses into carbon, carbon into oxygen, oxygen into neon, magnesium, and silicon. Fusion occurs in layered shells, like an onion skin, with heavier elements in the core. The energy released by element fusion counteracts gravity, preventing the star from collapsing. But this process has an end point. When the core begins to produce iron, the critical threshold is reached. Iron fusion no longer releases energy; instead, it absorbs energy, causing the star to lose its structural support and proceed toward collapse and explosion. The death of massive stars, the supernova explosion, is both violent and critically important. The extreme temperatures and pressures during the explosion enable the rapid neutron capture (R) process. Atomic nuclei rapidly capture a large number of neutrons in a very short time, forming extremely unstable isotopes that subsequently decay into stable heavy elements. Elements like gold, platinum, and uranium would be scarce to almost non-existent without supernovae. Diagram illustrating the R process and S process nucleosynthesis paths. Not all heavy elements require such violent processing. The slow neutron capture (S) process also occurs later in a star's life. In a gentler environment, the star uses convection to bring products from the core to the outer layers, slowly capturing neutrons over thousands of years to generate elements like strontium and barium, which are then carried into interstellar space by stellar winds. The material scattered by the dying stars enriches the interstellar medium, the vast space between stars. Millions of years later, this material, now enriched with heavy elements, participates in a new round of star and planet formation. Our solar system was born from a cloud of gas and dust that had been fed by previous generations of stars. The carbon in our bodies, the oxygen we breathe, and the iron in our blood were all forged in stellar furnaces that predate the Earth's appearance. Heavy elements can also be forged in even more exotic furnaces, such as neutron star mergers. When two neutron stars collide, they can instantly trigger a massive production of R process elements. The accompanying kilonova explosion exhibits a unique spectrum and light curve evolution. This extreme environment is truly a gold mine for nucleosynthesis. Stellar nucleosynthesis is also related to a star's metallicity. Stars with high metallicity have more complex initial compositions and a greater variety of fusion chains. In contrast, the universe's first generation of stars were composed almost entirely of hydrogen and helium, were massive, and had short lifespans, ultimately scattering the first batch of heavy elements into the cosmos via supernova explosions. Directly observing these nucleosynthesis processes is difficult. Our knowledge primarily comes from the fingerprints in stellar spectra. The spectral lines of different elements show their presence and abundance. For example, detecting signals of heavy elements in the spectra of distant stars is evidence that nucleosynthesis permeates cosmic history. Studying supernova remnants allows us to trace what happened during the explosion, and analyzing their elemental composition helps us reconstruct the origin of heavy elements. The significance of stellar nucleosynthesis extends far beyond the stars themselves. The water we drink, the silicon in computer chips, and the iron in our blood all originate from the life and death cycle of stars. In recent years, computer simulations have significantly deepened our understanding of the complexity of nucleosynthesis. Variations in rotation, magnetic fields, and mass loss rates all affect the production and distribution of heavy elements. Simulations also help explain why element abundances vary significantly across different regions of the galaxy. Kilonovae are among the most extraordinary and creative explosions in the universe. They originate from the merger of neutron stars, violent and glorious, yet they are the birthplace of the rarest heavy elements. To grasp the significance of a kilonova, one must first understand neutron stars. They are the remnants of massive stars after a supernova explosion, consisting almost entirely of neutrons. Their density is so high that a sugar cube-sized piece of neutron star matter could weigh 1 billion tons. Although only about 20 kilometers in diameter, they can contain twice the mass of the Sun. In rare cases, two neutron stars form a binary system. Over millions to billions of years of gravitational dance, they slowly lose energy by emitting gravitational waves. Their orbits continuously tighten until they merge. In the final moments, they spiral around each other at near-light speeds, and the energy burst from the merger creates the kilonova we observe. Unlike supernovae, which are primarily driven by stellar core collapse, the light from a kilonova comes from the radioactive decay of heavy elements forged in the merged matter. The explosion covers a wide spectrum from gamma rays, X-rays to visible light, and infrared. The most distinctive feature is the R process nucleosynthesis that occurs in an extremely short time, where a large number of neutrons are rapidly captured, causing atomic nuclei to transition into highly unstable isotopes that subsequently decay into stable heavy elements. A single kilonova event may produce more gold than the entire amount ever mined on Earth. The 2017 event was a landmark. Gravitational wave detectors first captured a neutron-star merger, and simultaneously, multiple telescopes in the electromagnetic spectrum tracked the kilonova signal from the same source. This multi-messenger observation directly confirmed that neutron-star mergers indeed forge heavy elements. The gravitational waves not only told us that a merger occurred but also carried information about the mass, spin, and orbit of the merging neutron stars. By analyzing these waveforms, scientists can infer the equation of state of neutron star matter, extreme physics that cannot be reproduced in terrestrial experiments. Furthermore, kilonovae are considered cosmic standard sirens. By combining gravitational wave and electromagnetic signals, we can directly measure the source's distance, thereby independently estimating the Hubble constant, offering a new path to resolve the Hubble tension, the discrepancy between measurements obtained by different methods. The debris ejected from the merger is not isotropic. Some material is spewed out in relativistic jets that trigger short gamma-ray bursts, while slower ejecta dominate the time-decaying kilonova light curve in visible and infrared wavelengths. Numerical simulations blend fluid dynamics, nuclear physics, and radiation transport to predict the kilonova's light curve and spectrum under different conditions. Cross-referencing these predictions with observations helps us clarify the details of heavy element synthesis. Diagram showing the multi-messenger observation of a kilonova neutron star merger. From a broader perspective, kilonovae reintroduce heavy elements into the interstellar medium, which eventually enter new stars, planets, and even life. The gold in your ring and the platinum in your catalysts were very likely forged in an ancient kilonova. Next-generation facilities will push the detection range further and finer, helping us achieve a more comprehensive understanding of neutron star mergers and the cosmic origin of elements. The interstellar medium, ISM, is the sea of matter and energy that fills the space between stars within a galaxy. Far from being an empty void, it is a crucial component of the universe, influencing everything from the birth of stars to the evolution of the entire galaxy. Its composition, structure, and interactions are the keys to unlocking the operational mechanism of the Milky Way's grand workshop. The ISM is primarily composed of gas, with hydrogen constituting about 90% of the mass, most of the remainder being helium, and trace amounts of heavier elements existing as molecules, ions, or solid dust grains. Although dust accounts for only about 1% of the mass, it plays a disproportionately important role in many astrophysical processes. Dust is typically composed of silicates, carbon, or ice, and it can absorb and scatter starlight, creating the stunning nebulae visible in the optical and infrared. Another crucial component is cosmic rays, high-energy particles originating from sources like supernovae, which travel through the medium at near light speed, interacting with gas and dust, driving the chemical and physical evolution of the medium. The interaction between cosmic rays and the ISM also produces gamma rays, serving as tracers for high-energy processes. The ISM can be divided into different phases, each with distinct temperature, density, and physical conditions, existing in a dynamic balance and constantly exchanging matter and energy. The coldest and densest are molecular clouds, with temperatures only slightly above absolute zero and densities reaching hundreds to thousands of particles per cubic centimeter. These are the birthplaces of stars. Warmer are the diffuse atomic clouds, with temperatures of a few thousand Kelvin and densities of about 1 particle per cc. Ultraviolet radiation from nearby hot stars ionizes the hydrogen within, forming the ionized hydrogen regions HII that glow brightly in the optical band. The hottest and most tenuous is the hot ionized medium, with temperatures reaching millions of Kelvin, heated by supernova shockwaves, which inject massive amounts of energy into the medium. Diagram illustrating the different phases of the interstellar medium: ISM cold, warm, hot. The boundaries of these phases are not fixed. Supernovae, stellar winds, and galactic dynamics continuously redraw their map. Supernova shockwaves can compress neighboring molecular clouds, triggering star formation, or conversely, dissipate the clouds, inhibiting star formation. A delicate balance of creation and destruction is the essence of the ISM. The ISM deeply affects the propagation of electromagnetic radiation. Starlight passing through the medium is absorbed, scattered, or re-radiated at other wavelengths. This is particularly noticeable in the ultraviolet and visible light, but the absorbed energy is re-emitted in the infrared, providing clues about the temperature and composition of the dust. Radio astronomy is the primary method for studying the molecular components of the medium. Characteristic radio lines from molecules like carbon monoxide (CO) and water help us map the distribution of molecular clouds. Observations reveal that the medium exhibits fine structures like filaments, clumps, and cavities. These are shaped by a combination of gravity, magnetic fields, and turbulence. Magnetic fields, though harder to grasp, are vital. They regulate the motion of gas and dust and participate in the star formation process. Observations of polarized light and radio emissions show that magnetic field lines thread through the ISM, affecting the shape and dynamics of the clouds. They can also trap cosmic rays, forming feedback loops that influence the energy balance. The ISM is also a chemical laboratory. Besides hydrogen and helium, a rich variety of molecules can form, even including organic compounds like methanol, formaldehyde, and even amino acids. This suggests that the seeds of life are not rare in the universe. Supernova remnants are one of the most spectacular structures in the medium. The outer layers ejected by the explosion collide with the surrounding gas at incredible speeds, creating shockwaves that heat and ionize the medium. Remnants can persist for thousands of years, injecting heavy elements like carbon, oxygen, and iron into the medium. They are crucial for the formation of subsequent stars and planets and highlight the ISM's role in cosmic chemical evolution. The ISM and overall galactic dynamics are equally intertwined. Density waves in the spiral arms can compress the medium, triggering star formation waves. Hot gas fountains out of the disk plane into the halo and cycles back, continuously refreshing the medium. Despite continuous progress, mysteries remain. Why do some dark clouds heavily obscure starlight yet barely radiate themselves? They may contain vast amounts of cold, dense gas, but their specific properties and role in star formation are still unclear. The origin of interstellar turbulence is also a challenge, possibly driven by a combination of supernovae, magnetic fields, and galactic rotation, but accurate modeling remains difficult. Comparing the ISM in the Milky Way with that of other galaxies can also reveal commonalities and differences. For example, the medium conditions in starburst galaxies differ greatly from those in quiescent galaxies, reflecting different evolutionary paths. Since Albert Einstein's general relativity predicted it in 1915, gravitational lensing has become a direct demonstration that gravity not only acts on matter but also bends the geometry of space itself. It has also become a key tool for studying the universe's most elusive components and the early history of galaxy formation. Image illustrating gravitational lensing. The core mechanism is that massive objects warp the spacetime around them. As light passes through this warped space, it follows the curved path, causing background objects to appear distorted, magnified, or even multiplied in observation. The type and degree of these aberrations depend on the mass, shape, and distribution of the foreground lens, as well as the relative alignment of the observer, the lens, and the background source. Gravitational lensing is broadly divided into three categories: strong lensing, weak lensing, and microlensing. Strong lensing occurs when the three components are nearly perfectly aligned and the lens's gravity is sufficiently strong, resulting in pronounced effects where the background source appears as multiple images, stretched into arcs, or even forming a complete Einstein ring. Strong lensing is common in massive galaxy clusters and not only provides stunning photographic evidence for general relativity but also allows us to map the distribution of the lens's invisible dark matter. Weak lensing is more subtle. It does not produce clear multiple images or long arcs but causes a slight stretching of the background galaxy's shapes. Individual signals are too small to be noticeable, but by statistically analyzing a large sample, we can infer the distribution of dark matter on the large scales of the universe. Weak lensing is also one of the most powerful tools for studying dark energy, the mysterious force driving the universe's accelerated expansion. Microlensing occurs at the smallest scale. A single star or even a planet can act as the lens. It usually does not cause resolvable shape distortion but temporarily brightens the background star. This technique has helped us discover many exoplanets and also captured the gravitational traces of rogue stars and black holes. The applications of lensing effects in cosmology are wide-ranging. One of the biggest contributions is mapping the distribution of dark matter. Dark matter neither emits nor absorbs light, but its gravity influences the path of light. By analyzing strong and weak lensing patterns, we can map the dark matter skeleton. Lensing also acts as a natural telescope, magnifying extremely distant and faint early galaxies to a point where they can be studied. The Hubble Space Telescope has used the lensing effect of galaxy clusters to observe young galaxies less than a billion years after the Big Bang. Using lensing, researchers can also weigh celestial objects. The degree of light bending is directly related to the mass, which is particularly valuable for measuring hard-to-weigh objects like distant galaxy clusters and isolated black holes. Image comparing strong lensing arcs, multiple images, and weak lensing shear distortion. Lensing is also a crucial proving ground for general relativity and modified gravity theories. By comparing observed lensing signals with theoretical predictions, we can test Einstein's equations on scales ranging from stars to the cosmic web. Systemic deviations might hint at new physics. An interesting phenomenon revealed by lensing is time delay. When the light from the same background source is bent into multiple paths, the light arrives at different times because the path lengths are different. Measuring these time delays can be used to estimate the Hubble constant, providing an independent cross-check for other methods, which is highly significant in the current Hubble tension debate. Unlike ordinary matter composed of protons, neutrons, and electrons, exotic matter refers to a range of hypothetical materials that defy conventional understanding and possess counterintuitive properties, such as repulsive mass or negative energy. While not yet directly observed, their theoretical implications are profound enough to overturn our understanding of the universe, from the nature of dark energy to the possibility of faster-than-light travel. One of the most anomalous concepts is repulsive mass. If it exists, it would accelerate in the opposite direction of the applied force. This type of matter is considered a necessary component for stable, traversable wormholes. If wormholes exist, they might allow for effective faster-than-light travel or instantaneous passage. Negative energy is equally crucial. In quantum field theory, the Casimir effect is believed to involve a difference in vacuum energy that has been verified in the lab. While this is not equivalent to the existence of negative energy on a macroscopic scale, it provides a tantalizing clue that negative energy might play a role in the fabric of the universe. Diagram illustrating the concept of a traversable wormhole stabilized by negative energy, exotic matter. Exotic matter is also a popular candidate for explaining dark energy. Dark energy accounts for about 68% of the universe's total energy density and possesses negative pressure, which drives the universe's accelerated expansion. If it is a form of exotic matter, its nature would deepen our understanding of cosmic expansion and the ultimate fate of the universe. In the context of quantum gravity, exotic matter might also be a missing piece of the puzzle connecting general relativity and quantum mechanics. Some speculate it could somehow stabilize the spacetime quantum foam at the Planck scale, avoiding the singularities at the center of black holes and at the beginning of the universe. However, the difficulties are immense. There is currently no direct evidence, and many of its properties conflict with existing physical laws. For example, repulsive mass would challenge the standard interpretation of Newton's second law, and its existence might also render the vacuum unstable. Experimentally, researchers often approach it through indirect evidence, looking for signs of non-standard matter in high-energy environments like galaxy centers, or searching for new particles and interactions beyond the standard model in particle accelerators like the Large Hadron Collider. Even without concrete discoveries, these explorations continuously tighten the parameter space where exotic matter might exist. In more romantic scenarios, exotic matter is utilized in the concept of the Alcubierre drive, which achieves effective faster-than-light travel without violating relativity by contracting space in front of the spacecraft and expanding it behind. However, this concept requires negative energy density as fuel, so its success hinges on whether exotic matter exists and can be controlled. It also frequently appears in discussions of time travel. If wormholes can be stabilized by negative energy, they could theoretically form closed time-like curves, allowing travel to the past or future. Though highly controversial, this demonstrates the astonishing potential of exotic matter to reshape the boundaries of space and time. In astrophysics, exotic matter is used to discuss the black hole information paradox, and alternative explanations for mechanisms like particle acceleration in jets. In the extreme conditions inside neutron stars, some also hypothesize the existence of forms of exotic matter, such as quark-gluon plasma or strange matter. In the multiverse picture, exotic matter is even considered a bridge between different universes. While still highly speculative, it continuously expands the limits of our imagination regarding the fundamental nature of reality. That concludes today's sharing of knowledge. We wish you a beautiful dream and a wonderful day. We'll see you next time.